Alright, so in the previous video we proved the fundamental theorem of arithmetic, which just basically says that if you are given a positive integer greater than 1, then it has a factorization as a product of some primes in an essentially unique way. For example, you can look at this integer 360. Now, if one tries to write this as a product of primes, then one gets this. So, 3 2's appear, 2 3's and 1 5, which shows that the primes that appear in such a factorization, all of them need not be distinct. Some of them may be the same. So, you can of course collect the like terms, the like primes, and replace them with a single power. And this gives rise to this next corollary, which is just simply another way of stating the fundamental theorem of arithmetic, and it's naturally this: any positive integer n greater than 1 can be written uniquely as a product of primes. That means uniquely in a canonical form, which looks like this: n equal to p1 to the power k1 times p2 to the power k2 and so on, pr to the power kr, where for I varying from 1 to r, the ki's are positive integers and the pi's are distinct primes such that they are arranged in an increasing order. Well, the original primes that appear in a factorization need not be distinct, which you can see from this example, but once you write the canonical form, there the primes are, that are appearing, that they are distinct, because we are collecting all the like primes and we are making a single power. Similarly, we are collecting some other like primes and we are making a single power. So here the pi's are distinct, and of course, because we can just change the order as we like, so we can always arrange things in this way, where the primes appear, that is, they are increasing. Okay, that way also we can write. So this is called a canonical form, the canonical factorization of the positive integer n. Now, some other examples are also given of such factorization. For example, well, 360 we have already written the canonical form. Two others have been given in the text. 4725 has this canonical factorization, three cube times 5 square times 7, and another number is given which unfortunately is wrong. It's a printing mistake. Okay, the actual number should be 17,640. In the text it's given as 17,460, which is wrong. I'm saying because the factorization that is given matches with this one but not the one given in the text, and the factorization here is 2 cube times 3 square times 5 times 7 square. You can verify this. Okay, this turns out to be 17,640 and not 17,460. So this way any positive integer greater than 1 will have a unique canonical factorization of that form. Now after this, the author says that this uniqueness should not be taken lightly, because there are number systems in which this uniqueness is not there, and such an example is the set of all even positive integers. And so on. Now in this set also of course we have our multiplication operation, so that if you multiply two positive integers that are even, then the result is also an even positive integer. So E is closed under multiplication. Now we can define a kind of primality for elements in E. Well, you would say that or the only prime in E is 2. Yes, that is true, but we are going to define a new kind of primality for the set E only. We define a positive even integer, that means an element of E, to be an E prime. E denotes evenness, which all the elements in capital E have. So such an integer is said to be an E prime if it is not a product of two positive even integers. Do you see what we have done here, or what the author has done here? What is our ordinary definition of primality? That is just simply primality. We say that a positive integer n greater than 1 is a prime if n cannot be written as a product of two positive integers, both of which are greater than 1. A similar thing has been done here in this definition. A positive even integer is said to be an E prime if it cannot be written as a product of again two such things. So they are similar, these two definitions. So what are the E primes? Hence, the E primes are 2, 6, 10, uh, 14 and so on, and the even integers that are not E prime. If you want, you can call such integers E composite. 4, 8, 12, 16, and so on. You can see what we have done here to recognize the E primes. We have considered the odd multiples of 2. 2 times 1, 2 times 3, 2 times 5, 2 times 7, and so on. So that being even numbers and positive, these belong to the set E. Fine. But at the same time, you cannot write them as a product of two even integers. Why? Because then the integer, the entire thing would be divisible by 4, two even integers. This, however, is this is not that kind of number which will be divisible by 4. It's divisible by 2, fine, but then another 2 will not divide that thing, that is 2m plus 1, simply because it's odd. And to find the E composites, you just consider the remaining numbers. These are also even and positive, so that they also belong to E, but you can clearly see that each one of them is a product of two even positive integers. So that's why they are the E composites. Fine, but so what? Now in this E also, we can of course factorize every element as a product of E primes, just like we can factorize ordinary integers as products of ordinary primes. Similar factorization is available here in this system. Note that, however, that uniqueness that we have in the fundamental theorem of arithmetic is lacking in this system. Note that the number 60 of course belongs to E, it's an even positive integer, and it can be factorized as a product of E primes in different ways. One of them is 2 times 30. Are 2 and 30 both E primes? 2 is an E prime that we have written here. 30 is an E prime because it's an odd multiple of 2. But at the same time, we have this factorization also. 6 is an E prime and so is 10. So you can see that the E primes appearing in these two factorizations are actually entirely different, which is not possible in the ordinary factorization of ordinary integers as products of ordinary primes. So that's why this uniqueness is not available everywhere. And why do we not have uniqueness here? That's because we do not have that theorem 3.1. It is not true in E. The lack of this uniqueness in the factorization is is due to the fact that theorem 3.1 is not true in E. So theorem 3.1 was that result which says that if P is a prime, that means ordinary prime, and it divides a product AB of two integers A and B, then it should divide either A or B. This is not possible here, and the counter example is this. The E prime 6 divides the product of these two elements coming from E, but 6 divides neither 2 nor 30. There is a very subtle thing here. Let me complete the sentence, then I will say what it is. But 6 does not divide 2 and 6 does not divide 30. I know, I am almost sure that you would immediately object to this. You would say no, 6 divides 30. But there is something that should be considered carefully. You see, when you are in the ordinary, because we are not considering negatives here, so let me just simply take the set of natural numbers where we do not include 0. Okay. We have this thing on one hand. On the other hand, here we have the set E. Now, when do we say that an ordinary integer, for us positive integer, because we are not considering negatives, an ordinary positive integer divides another ordinary positive integer? When do we say this? For example, 2 divides 4, but 2 does not divide 3. The reason 2 divides 4, or the definition of this divisibility relation, is this: 4 is equal to 2 times 2. Well, you won't see the distinction between these two and that two here. Let me take another one. 2 divides 6. Why? Because 6 is equal to 2 times 3. So 6 is a multiple of 2, where that other number actually belongs to this set. 3 belongs to n. That's why. Because if you do not consider this condition, if you do not have this restriction, then you can just divide anything by anything, because 3 can be written as 2 times 3 over 2. But because of this equation, we do not say that 2 divides 3. And the reason is that this rational number 3 over 2 is not an integer. It does not belong to n. Now you look at this. 30 is 6 times 5. Fine. So 6 divides 30 in the system n. But 6 does not divide 30 in the system E, because 5 does not belong to E. So that's why we have this non-divisibility. So you see that the E prime 6 divides the product of these two elements from E, but it divides neither of them. Because of this, we do not have uniqueness in such factorization. That's because while we were proving uniqueness in the ordinary factorization of ordinary integers as products of ordinary primes, we used this theorem, which now we do not have in this system. So that's why that uniqueness is something special. Okay, it's not available everywhere. Now the section ends with another application of the fundamental theorem of arithmetic to a situation with which we are, almost all of us are familiar, namely the fact that square root of 2 is an irrational number. Pythagoras gave its proof, right? So we are now going to see that thing, and that's where this section ends. So its theorem three, and it's due to Pythagoras, and it's just that the number square root of 2 is irrational. Pythagoras and his school and the people who studied these things, they believed that rational numbers are what we have and there is nothing else. So the discovery that this number is irrational was kept as a secret. Okay, it was something that they were not very fond of. In fact, they really disliked it, but it is what it is. Okay, this number turned out to be something that is irrational. So they felt that this is like an omen. It's something bad that people should not know. So they kept it secret, but later it came out, and someone was murdered also, I think, because of this. The beginning is just like what you have seen in many places, probably. Suppose this is rational, then by the definition of rational numbers, it can be written as a ratio of two integers, where A and B are integers and they are relatively prime. Well, this relative primality is not necessary, but we can assume this. Okay, why? What is the reason? You know that a rational number has many different representations, and there is one among those representations which satisfies this property. What I am trying to say here is this. Say, let me just take a very simple example. You have this rational number 1 over 2. In its place, you can also write 3 over 6 or minus 2 over minus 4. You can, this way you can write many things, okay, as many as you like. Infinitely many different representations for the same rational number. But the difference between all these representations and the first one is that in the other representations, the numerator and denominator are not relatively prime. Their greatest common divisors are not equal to 1. However, for this one it is so. Well, there is another one also, minus 1 over minus 2. Here also the GCD of minus 1 and minus 2 is 1. And such a representation always exists because in the other representations, whatever common factor you have between the numerator and denominator can be cancelled out, leaving you with such a representation. So, regardless of what A and B are, I mean, you can choose such A and B that are relatively prime. Now, if B is greater than 1, and there is one more thing, we can choose B to be positive. Why? Because if B originally is negative, you can just simply put the burden of negativity to A. You can raise it there. If originally B is negative, then you can write this in place of this. So now that B is negative, now minus B is positive. Whatever happens to A, I mean, it has been turned into minus A, we do not bother. Now, if it happens that B is greater than 1, then we can apply the fundamental theorem of arithmetic on B by the fundamental. I think I am losing ink. I need more. Just a moment. So by the fundamental theorem, B will have a prime divisor. There exists a prime P such that P divides B. Now, squaring both sides and manipulating the equation, we get 2b square is equal to a square. From this equation, you can clearly see that since b divides the left hand side, b also divides a square. Which implies b divides a square, but p divides b, and since divisibility is a transitive relation, so p has to divide a square as well. And so, because p is a prime, we have that theorem 3.1. P divides A. But now P divides B as well as P divides A, which means that A and B have P as a common factor. So the greatest common divisor should be greater than or equal to P, because P already is a common divisor. And this is a contradiction because P cannot be less than or equal to 1. and all these things are a consequence of the fact of the assumption that b is greater than 1, so it cannot be greater than 1. It must be equal to 1. Keep in mind, we have forgotten to write something, that namely that b is positive. I just said so, but you make it a part of the proof. Okay, you not only write that because of our assumption that root 2 is rational, that we have root 2 as a over b, where a and b are integers and relatively prime, but you also say that where b is positive. Okay, because of that and because of this contradiction, now b has to be equal to 1. But then square root of 2 is equal to a, or if you take square on both sides, you get 2 equal to a square. Okay, now from this equation you get, I mean, among other things, you also get the fact that a is positive. Now, being a positive integer, if a, well, if you feel like ending the thing here itself, that square root of 2 is an integer, that should not be true. However, why? There should be a reason. No? So that's why we keep going. We do not end it here itself. We want to argue a little more. Now, if a is greater than 1, ideally you should write that from this equation we conclude that a is positive. That means a is greater than or equal to 1. Now, if a is greater than 1, then again by the fundamental theorem of arithmetic, there exists a prime, let's call this one q, such that q divides a. But then q divides a square as well, which is 2. But q is a prime and q is dividing 2, which itself is a prime. So there is only one choice left to us, namely that q is equal to 2. Okay, but then what do we get from that? We get the fact that a is a positive, a is an even integer because q has been 2. So a is equal to 2k for some positive integer k. Hence, so now we can use this equation once more and have this, or after cancellation we get this. Which implies that 2 divides 1. And this cannot be true. This is not true. this is a contradiction. But that's not the end. Okay. This thing again is arising from this if condition. So that means that if condition should not be true. So A must be equal to 1 because A is already greater than or equal to 1. If it is not greater than 1, this is the only choice left. But then and this is again another absurdity. So where is now we have nowhere to go. We have come to a dead end. So that means something must have gone wrong. We have already taken care of all the ifs that appeared in the middle of the proof somewhere. However, you remember that in the beginning itself we started the proof with a supposition. That supposition hence must be false because there is nowhere else to go. Hence, the initial supposition is wrong. That is, this must be irrational. And now the proof is finally over. Now you may feel like this proof is quite long and the one that you may be familiar with is much shorter. Well, that is actually the case. But it shows that we can use the fundamental theorem of arithmetic also to have a proof. However, a much shorter proof is still there in the text, which appears after this, just as a, before the section ends, it's just written here. We can also have this much shorter proof. Where the beginning is same, suppose for some integers a and b with their GCD being 1. But then we know that when two integers are relatively prime, an integer combination of them is equal to 1. So 1 is equal to AR plus BS for some integers R and S. Now root 2 can also be written as root 2 times 1 which if you use that expression, it becomes AR plus BS. So this becomes root 2A times R plus root 2B times S, and that is equal to, well, now we look at this. If you multiply on both sides of this equation, well, this equation actually, if you multiply on both sides by square root of 2, you will get 2b is equal to square root of 2a. So if you use that here, then you get 2br. And what is square root of, here we directly have plus as, which is an integer. An integer, and this is not possible. Why is it not possible? You may be, you may have to justify this. No, we feel like this is not possible, but why root 2 is not an integer, that follows from the last part of the previous proof. You can use those arguments and complete the proof, or if you feel like this is something that we already know, which needs no further explanation, you can just end it here itself. In the text also, the author has ended it here. So that's how the section ends. In the next number theory video, we are going to start solving the exercises on this section. So that means this is all for tonight's video, and our next update is this coming Friday, and on Friday we are going back to graph theory, where we left one problem partially solved. So we will complete it and see other exercises also. So see you on Friday with that. Until then, this is me, Lucifer, from A Mathematical Proof. Have a nice night.